Good morning, everybody. Great to see so many familiar faces. Blast from the past. What I'd like to do in the next 20 or so minutes is talk to you about the Future Energy Exports CRC, where we're at and what we're planning to do. Hopefully by that stage, you'll have a sense of how we're going to work and the opportunity that I think the CRC represents, particularly for Western Australia, to take a lead in the next major initiative in energy that the world, I think, is everywhere looking to take advantage of, and I think we've got a particular advantage. Now, the slides got printed with all the reserve slides at the back, so I'm not going to go through every single one of those. You'll be pleased to know. If you have any questions, you can look up, or need to think of a question, you can look up the back and I might be able to answer them then. Okay, so as Bruce said, so the Future Energy Exports CRC has sort of two missions. One, and they are connected and related to one another. First is to ensure that our vital LNG exports remain competitive. And although we are the #1 exporter in the world as of last year, that's not necessarily just going to continue happening by magic, as I'll explain in the next slide. So we've got several pressures that Zach sort of alluded to that we need to stop. We can't afford to rest on our laurels, and we need to continue work to make sure we get the most out of that very natural endowment that Australia has been blessed with. The other, though, is to take advantage of the opportunity to grow a hydrogen export industry. Again, we're not the only country in the world that sees the opportunity. All of the competitive countries like Qatar, Russia, that have natural gas reserves, they also see the opportunity, and arguably will not be as diligent necessarily as doing it in a way that's will respect the environment. So it's not just important for us to do well in that case, but also for the world if we're trying to move to this decarbonized energy basis. So what is the challenge? Sort of three challenges / opportunities. Australia has sunk a lot, invested a lot of money into building this world-class LNG industry, but it hasn't been cheap. And analysis by Wood Mackenzie shows that in circa around 2016-17, the cost of LNG from Australia was about double that of cost of LNG from the United States, and an order of magnitude larger than the cost of LNG out of Qatar. And as when this slide was put together, the gas price was pretty low, and it's come down even further. The world is awash with LNG. It is now basically a commodity that people are opportunistic when it comes to spot markets and the like. So for Australia to continue to capitalize on its investment, we've got to find ways of lowering the cost of LNG production, using the assets we already have built to get more out of them in particular. But we have to do this and at the same time reduce the carbon footprint of the Australian community in particular. Shareholders are applying a lot of pressure on Scope 3 emissions to the major exporters, and internationally the industry needs to reduce emissions. All sectors do. And one of the problems is that we've got to both educate the public on, but also do something about, is whilst the switch from coal to gas in Asia Pacific is actually what matters, often there's a local focus on the fact that there's been a small spike in our emissions because the LNG plant just started up and has had a disproportionate impact. So in addition to educating the public, we have to find ways to lower the CO2 emissions whilst also getting more out and more productivity out of our system. And then, of course, the longer term opportunity is that the countries that are buying our LNG, Japan, Korea, are looking to switch to hydrogen. And we would like to supply them with that hydrogen. The challenge, though, is cost. If you take blue hydrogen, which is hydrogen that comes from natural gas, there's steam methane reforming, that's at least 2 to 3 times the cost of the energy in LNG. And if you go to renewable hydrogen, you're something like 8 times the cost. So getting that cost curve down in the next 10 years is going to take innovation. It can be done, but we have it's not a simple matter, and you shouldn't buy into the hype that it can just be done tomorrow. Now, people often say to me, why would you, particularly if they're not chemical engineers, combine LNG and hydrogen? What have they got to do with one another? Probably the audience here understands that a little better, but it's not actually about the technical similarities between these energy vectors. It's the workforce and the skills. There's no way a hydrogen export industry from Australia is not going to take advantage of the people who've driven the LNG industry here. So transitioning that workforce is particularly important, similar engineering and practice, and also the business relationships. The shipping routes are important, the jetties, those sorts of things. So in fact, my argument is that the fact that we have an existing world-leading LNG industry gives us a natural advantage in the race to become a global hydrogen exporter. So this diagram looks at what the CRC, what's in the frame or in the scope of the CRC. We're not looking per se at the production of the various types of energy, but how they are used to sell and export that energy. So there are two major columns, LNG and blue hydrogen on the left here, green or hydrogen on the right. Starting on the left, we're looking at ways to increase the efficiency, the throughput of LNG exports while also offsetting their emissions. So figuring out ways to do carbon capture more efficiently from and sequestration more efficiently from LNG production, reducing fugitive emissions and the like. Really lowering the footprint is a key activity for the centre. But similarly, we want to look at the cheapest way of making hydrogen today, which is steam methane reforming, coupling that with CCS. So none of these technologies is particularly innovative, and they've been demonstrated by themselves, but it's when you integrate them and figure out how you really drive the cost down so that integrated technology becomes competitive, that is a key challenge for us. Once you've got the hydrogen, you've got to figure out how to get it to your customers overseas. And there are multiple options, and we are agnostic about the vector, the energy vector, whether it's ammonia, liquid hydrogen, or a liquid organic hydrogen carrier. We think that will very much depend on the market, who's buying it. So if you're doing base load power, then ammonia does sort of probably make sense. You're just going to burn it. But if you're supplying transport infrastructure where very high purity hydrogen is needed for the fuel cells that are going to go into vehicles, then it might be worth the extra cooling energy and difficulty of making liquid hydrogen. And if you're going to be working in regional areas where handling fluids is not straightforward, and there's not the infrastructure to do it, then liquid organic hydrogen carriers like methanol or methocyclohexane, that might be the way to go. We'll also be looking at renewable hydrogen, looking at ways, for example, to increase its efficiency. Again, it's often now about systems integration, large scale. Solar is an inherently generates a DC electricity, electrolyzers and the grid often work at AC. Every time you have a switch between those two types of current, you have losses of energy. So figuring out how to minimize those energy losses is one of the research areas. Also using low quality water, brackish water, so we don't have to have that competition between water supplies and energy. We have several mining and also electricity providers who are interested in how hydrogen can be used for grid firming and also to displace diesel on mine sites, and then ways that we can export that and make sure we don't run into the same sorts of problems that the East Coast has encountered when it comes to gas reservation, domestic use of gas versus export of LNG. We don't want the same problem to happen with hydrogen in the coming years. We have two cross-cutting themes. Digital technologies will, Industry 4.0, offer the potential to have the sort of the quick wins, the low-hanging fruit, where we, if we can get these technologies to realize their potential by allowing them to talk to one another. So often digital control systems, they can do a lot, but one system can't talk to another by design because the vendors don't want you to be buying their competitor's product. But actually, that's nothing fundamental, and our team is developing standards. We have a new Industry 4.0 test lab, which the Department of Industry have funded and will be launching later this month at UWA and also in St. George's Terrace. And then our fourth theme, it doesn't matter if the technology is perfect, if you don't have the market well characterized, the policy settings, regulations correct, and social license, then industries cannot get off the ground. And so that's our fourth R&D theme. Okay, so one of the things that's different about cooperative research centres is that they're actually independent from the university. So a bit different to the ARC centres and the chairs that have been run out of UWA before. The Future Energy Exports CRC is actually a not-for-profit company that is independent of the university, although UWA and others, universities as well as the industry partners, can be members of this not-for-profit. So we have a board of experienced industry professionals, and we will be filling that out over the next few months to probably 5. An executive team, myself, CEO, Mike Johns is the research director, and most of you know Jill Stajua, she's the Chief Operating Officer. The research directors are led by senior academics at the university. So at Curtin, we have Professor Vishnu Parikh and Professor Craig Buckley leading the hydrogen program. Program 1 is the LNG stream. Program 3 is the digital technology stream. That's led by Professor Stumpner at University of South Australia. And then Program 4, which is the sort of market and sector development, is co-led by academics at QUT. And we're fortunate to have Professor Ian McKinnon also at QUT, who is the strategic advisor on hydrogen to the Queensland government. So we've set up this company and essentially the way it works is that this set of collaborators will be investing over 10 years, $38 million. And that is matched by a Commonwealth grant of $40 million. And we got the first payment of that last Thursday. So one payment down, 39 to go. Obviously, the Commonwealth reviews progress and makes sure we're delivering on the R&D that we've said we'd commit to. So that's our challenge as a management unit. But you can see that we have the major LNG organizations. We have ITM Power, which is one of the world's leaders when it comes to electrolyzer construction and sales. Also talking to Linda, who have a JV with ITM. The shipbuilding companies, Wood. We've got a range of smaller operators on beaches, relatively active in the East Coast and very focused on the digital interoperability challenge. Horizon Power and Mineral Resources working closely with us in that space of energy and electricity provision and mining. The state governments are very strong. The government of Western Australia is our biggest supporter. These are the universities that are involved, plus international collaborators in Japan and China. And a key feature of what we're trying to do is do R&D at a scale which allows it to be deployed, go from the lab quickly into actual practice. So industrial scale innovation is sort of a catch phrase, and we've got several facilities around the country to help us do that. QUT, for example, has a concentrated photovoltaic array, which is then coupled to a set of electrolyzers to generate renewable hydrogen at about 200 kilowatt scale. So it will be driving many of those projects. We have Industry 4.0 test labs at Swinburne, UniSA, and in Perth, which will help drive our digital technologies program. Biomass gasification facility actually at Curtin, just across the road from ARC there. And we're building, we hope to build the Futures facility, which I've talked about before, and I'll go into where we're at now because we're getting very close to the point of being able to take an FID. So I think of this as a foundation project for the CRC, the LNG Futures Facility. For those of you who haven't seen a video, I think it's worth a look. It's the Premier and Chevron CEO Mike Wirth at Shanghai last year at LNG 19, explaining why it's important. The cartoon video is shown here. The idea is that you have a small scale, or the original idea is you have a small scale LNG plant which is not there to make money or to make LNG, but rather to provide common user infrastructure to test out and demonstrate new technologies, whether they're sensors, mixed refrigerant compositions, new ways of recovering valuable compounds from the gas. We did a pre-feed study in 2018, identified this location which the state government has leased to us for the next 10 years, which is right next to Compressor Station 10 on the Dampier to Bunbury pipeline. And this study, as well as the feed that we've done, has been funded by NERA, Chevron, Hyundai, Shell, and UWA, and Mineral Resources Energy has put in a lot of in-kind work and continues to do so. So last year, and at the moment, we've been doing the feed, working with Clough to generate something like 197 documents, which, although it's a small project by many of this, by the scale of many that are in this state, it's been quite an interesting and excellent learning experience for myself. So we've, in addition to, I won't go through all of these items, but figured out exactly how the process units will be aligned, what they are, who is the vendor, how we're going to tie into them, what's the instrumentation that will allow us to get better data quality than can currently be obtained from existing plants. And of course, the key concept is, you might say, well, we've got all these plants, what do we need this one? Those plants they have a task and they're not to be mucked around with. You can't take and demonstrate a technology. This one will be turned on and off all the time and deliberately disrupted and operated in modes that you shouldn't operate it in from a strictly operational perspective, because you're trying to see if things work better in the way we think they might. This is sort of more on the way it's laid out. The LNG train will sit here. This covered area would be for where you would do much of the R&D plugging into that train at various stages. I'll talk about that more. The key other feature that the state government is interested in is its unique training capability. So this would be, currently the best facility is ACEPT, which is air and water still, at up to 8 bar. Nothing with live hydrocarbons or high pressures. And as I said, the instrumentation here means we can do a lot better job of actually rigorously confirming whether our models are right or wrong. But we need to go beyond LNG, part of the Future Energy Exports CRC, and integrate hydrogen. And so I'm going to finish off with the discussion of what we want to do there. So this is a PFD which shows the existing LNG train taking about 10 tons per day of gas from the pipeline. We have a recycle, so we don't actually have to spend that much on gas. We can send it back to the back to the pipeline if we like. These tie-in points for the various types of LNG R&D, and you can see that we've got the ability to take a stream and test out hydrogen conversion technology. So you might be familiar with the Hazer process, another spin out from UWA, where they crack the methane and create graphite and hydrogen. Although they have had a recent announcement, they're moving forward with a pilot, but this facility would allow that, if it existed, would allow that pilot to proceed much cheaper because they wouldn't have to build all the other infrastructure. And then once you've got the hydrogen, what do you do with it? Well, you could look at all these technologies in terms of making the various transport vectors, as well as perhaps providing fueling station demonstrations, certification for handling. The whole workforce needs to be trained, right, in how to work with hydrogen. So we're looking at several different options here, including electrolyzers and liquefaction, steam methane reforming, as well as bus trials and grid firming services. So let me talk about them a little bit further. So one of the options we're looking at is the integrated modular steam methane reforming system with CCS from wood. It produces about 5 tons per day. So actually, the main challenge with this system is that it's like it will take all of the gas from that's currently designed and turn it into hydrogen. There's nothing really smaller. That's one issue. But about 25 bar and 41 degrees C with the CCS. About $20 million for that unit is what have been indicated, an indicative cost, ex works. and again would easily fit into that space we have for tie-ins. Another one we're looking at with our colleagues at ITM is electrolyzers, in particular this 2 megawatt unit, which would represent one of the bigger hydrogen electrolyzers that's actually been installed. You'd need, we'd buy the electricity from Western Power, possibly ideally from renewable generation in Perth, and possibly at a cheap price, and then be able to sell the electricity back when the renewables aren't online, because of so not only grid firming services, but that sort of arbitrage, if you like. And this would generate something like 0.8 tons per day of hydrogen. So it's certainly easily handled and very pure, high purity. So good for fuel cell studies, bus trials. We'd look to sell the hydrogen, perhaps to support a hydrogen bus trial in Western Australia. And again, effectively, these are very compact units and would fit easily on our site. What we'd like to do is then take that hydrogen and liquefy it, again, cost dependent. Now, what I'm showing you here is state-of-the-art liquefiers from Lindy. These take about, or make about 5 tonne per day, these particular ones. So these are big, but they have got systems that would match the 2 megawatt electrolyzer that I mentioned, and that costs about $13 million. So that certainly would allow us to then do a lot of research into the hydrogen liquefaction, and particularly improve refrigeration cycles. How do we drive the energy cost in the way that's been done over many years in the LNG area, mixed refrigerants, other opportunities. Of course, one of the scientific challenges is this ortho-hydrogen to para-hydrogen conversion. So for those of you who don't know, hydrogen is actually a mixture that exists with 2 compounds that are quantum mechanically different. And it's pretty cool that at room temperature and above, it's 75% what we call ortho. But at low temperatures where you make liquid hydrogen, it's almost entirely pure para-hydrogen. And what's a problem is it's actually quite difficult to get the molecules flip from one state to the other. The energy associated with that is like 7 times the energy to boil off liquid hydrogen. So if you don't do it, or if you do it too quickly and they don't properly convert, then all your liquid hydrogen boils off. So it turns out in these liquefiers, they have catalysts embedded throughout the system to do that flipping. And that energy conversion challenge is certainly one where we're looking to minimize boil off during storage. And speaking of boil off, again, just to show you some of the overlap between LNG and liquid hydrogen, we've been working at the ARC Centre for LNG Futures with Samsung Heavy Industries, who make the LNG carriers, on better ways to model LNG boil off in storage tanks. So you might think, well, that sounds relatively simple, but what we understand from our colleagues at Samsung is that the vendors of the tanks that go into these ships provide them with charts which say, if your tank is this particular one, and here's a straight line correlation as a function of pressure, that's the boil off rate you're going to get. So if they change the pressure, they have to go to a completely new chart. It's certainly not coded in. And why does this matter? Well, they have to design these ships with boil off gas compressors on them. If those boil off gas compressors are too small, you've got a problem. If they're too big, then you're wasting capital, and not to mention the weight on the deck of the ship. So that's been their motivation. And we've developed with test facility here at UWA, plus some modeling, and then validated this model, a software package called BoilFast, which allows LNG boil-off rates to be described much more accurately, and working towards describing stratification. And of course, once the Futures facility is up and running, we'll be able to really optimize that model at a larger scale. But we could also, the basic equations are pretty similar for liquid hydrogen. You've got to change the thermodynamic model and the like, but there are some data out there from NASA, for example, and if you just fit, no fitting, not allowed to adjust parameters, that's rule 1. You take our model and you swap the equations of state, actually you do a pretty good job of matching that boil-off data that's available in the literature. But obviously, we need to go beyond this, and ultimately there are smart things you can do in hydrogen storage to even further minimize this hydrogen boil off. So just to wrap up, what's the business model? Okay, I'm talking about something that's, those unit operations. What we basically need to do is get $80 million to spend over the next 10 years or so. This chart shows you a net present value calculation for the facility. Capital costs of about 55 million is what the FEED report has come back at. Operational costs and the purchase of gas and electricity and a little bit of water, okay? But we'll be able to sell that gas back to the pipeline, probably at a similar rate to what we buy it at. We'll be able to generate hydrogen. Hydrogen sales are clearly worth something. Actually, the oxygen is also worth something, so you can sell that. Grid firming services mean we should be able to get the power essentially net free, because what we pay for power we can sell back in grid firming. And then we've got this $80 million of revenue from R&D and training. And you might think that's a bit optimistic, but actually, point one is the CRC would be a foundation customer. The CRC has $30 million. It's just that I can't spend it all in 1 year. I have to spend it over 10 years, but we'll be a foundation customer. So a bit like the agreements that LNG providers make over many years to at least do $30 million of R&D. And if you look at the R&D spend that just our group at UWA has done over the last 3 years, it tends to be about $3 million a year servicing the industry. So those two factors alone get you pretty close, and that's without any training and other activities. So we're pretty confident that given the uniqueness of this facility, that revenue will be generatable, in which case you would actually make a small profit on this system. And the state government would be a founding shareholder. We'll have a prospectus that allows us to call for other investors. I'm seeing the the new Vice Chancellor this afternoon. Next week, I get to see the Premier's Chief of Staff on this. So with that, hopefully I've explained to you what we're about and what we're trying to do, and that is to make Australian energy exports stronger and cleaner over the next decade.